Hey guys, the video that you just watched was made for the conceptual physics class, and so I need to emphasize some things for you guys in AP, just that I was able to leave out of the first one because they just didn't need it so much. So I kind of glossed over the introduction to the impulse equation. So I want to go through that one, make it a little more explicit here. Um, Now, the momentum equation, the P equals mv, that's in the AP gouge, but for some strange reason, the impulse equation is not, even though it's really, really useful, and you're going to be using it in your homework tonight quite a bit. Um, so again, the impulse equation here was how Newton arrived at this idea of how we change momentum. As we saw, you can change momentum by producing a large force for a short amount of time, and that will produce some change in momentum. Or you can do a small force for a large period of time and produce the same change in momentum. Now, delta MV, I kind of glossed over that in the first one, but this means change in momentum because P equals MV, P being momentum equals mass times velocity. Uh, so MV is kind of synonymous with momentum. Um, yeah, so to produce a change in momentum, you have to have a force times a time. Um, let's see. Now, this is a nice, neat slide, but that's where we are. Um, so here we are. It boils down to this, since impulse is a change in momentum. An impulse, another way to say that, is a force applied for some period of time. And that force applied for a period of time produces a change in momentum, so they are synonymous. An impulse is a change in momentum. This is kind of the mathematical expression of this definition that I gave you earlier. Okay, so here it is. The force times time equals change in momentum. Let's see. Um, I think we have it here. Yeah, here we go. You sometimes often see the change in momentum as delta mv or as m delta v, and these are synonymous. Okay, they truly do mean the same thing. The thought behind this one is that m times v, that's momentum. So you're talking about a change in momentum. The thought behind this one is that the way that you change the momentum of an object, like if you have a bowling ball or something, the only way you can make it change its momentum is by changing its speed. You can't change its mass, because if you change its mass, it's not the same thing anymore. So very often you'll see a change in momentum expressed as an m delta v. So a mass with where the velocity has changed. This is just kind of for historical interest. Um, Turns out that this F equals ma that we've been working with for so long, Newton wasn't a big fan of that. It may not, if it was mentioned at all in his famous physics book, The Principles of Natural Philosophy, it was only mentioned in passing. The impulse equation is the big kahuna as far as Newton was concerned. And when you think about it, it is pretty remarkable, because force is something that we can all understand. You know, it's a push or a pull. That's something that people have been able to understand for as far back as human history goes. Same thing with time. Everybody has some understanding of time, regardless of how you measure it. We do understand what time is, um, to some degree. But force and time are two completely different things. And then if you move on to the concept of mass, again, this is something that any human that's ever lifted something can understand and knows, and always has known. There's nothing esoteric or exotic about it, the concept of mass. But mass, again, is completely different than force or time. And then you throw in this force thing, velocity or speed. Again, that's something that anybody can understand. But these four completely different concepts, they seem to have nothing to do with each other, and yet somehow Newton was able to see a connection between them that is very revealing to how the universe works. So yeah, this equation here, the F times t equals delta mv, force times time equals a change in momentum. That's pretty profound, and that's a huge discovery. The problem with it is that that's hard to check. It's hard to do experiments where you can check all these things with precision. So what he did was he rearranged the equation a little bit, Actually, he didn't. It was people that came after him and were trying to actually test this stuff. And divided both sides by the time and divided both sides by the mass. So he got F divided by M, or we get F divided by M equals delta V over T. And you may recognize a change in velocity over a period of time. That is acceleration. That's the definition of acceleration. So that means that this side of the equation turns into A, and you could rearrange it and you get second law, F equals ma. So the second law is actually derived from the impulse equation, and the impulse equation is more fundamental. So go figure. Okay, let's see. That's more of the derivation there. Same thing. You can freeze it if you wish, but I kind of talked you through it already. There it is. That's the rest of it. So you can get the second equation, Newton's second law, from that. Let's see. I don't think this is. Yeah, these are the examples that we already went through. Okay, I want to show you one more thing on the clipboard here. Okay. What happens when we graph this stuff? And this is something that College Board and AP wants you to know about that the other class doesn't, so it didn't even come up. So suppose we make a graph of force versus time, force on the y-axis, time on the x-axis. So suppose we apply a force of 15 newtons and we keep it applied for 2 seconds. Okay, so 1, 2, 3, 4, 5 here. And then we stop. And we stop pushing on it, right? So this is 15 newtons times 2 seconds. And if we do the math there, we can see that the impulse or the change in momentum is 30 Newton seconds, or 30 kilogram meters per second. They're the same thing. That probably is worth mentioning here, that Newton seconds, which is kind of the units of force times time, is equal to kilogram meters per second, because Newton seconds is kilogram meters per second squared times seconds. Kilogram meters per second squared is Newton. So when you cancel out the seconds, you're left with kilogram meters per second. So they are equivalent. Conceptually, they're different ways of thinking of the same thing, but they are equivalent. Anyway, I digress. The point here is that if we apply 15 newtons for 2 seconds, we wind up with an impulse of 30 kilogram meters per second. Now, likewise, if we apply a force of 3 newtons, this would be 3 newtons, and we do it for 10 seconds. Let's see, the 10 comes out to here. There we go. And then we stop pushing. This is 3 newtons times 10 seconds. This is also 30 kilogram meters per second. It's the same impulse. And it shows up on the graph as area under the curve. So the area under the curve is impulse. The area under a curve of force times time, of a force time graph, is impulse. I took this a little bit too far. This is actually the origin here. And then we have the area under this curve. And if you count the squares, there's 30 squares under this one. There's 30 squares under this one. Comes out to be the same. Again, that's something that AP and College Board wants you to know. Doesn't have to be constant things. It can be changing force, where for some reason, the force increases like this and then stops. Same deal. The area under the curve will tell you the change in momentum that results because of that impulse. Anyway, that's it. That should be enough to get you going, and we will see you next time.